In this video we're going to have a look at car ignition coils and the possibility of using ones which are sold as 12 volt in a 6 volt electrical system. And the reason I'm keen to try this is because the Jeep is 6 volt and I want to keep a spare coil in it just in case. And if you buy a 6 volt coil, it's about $30 to $50, and chances are I'm probably never going to need it. So I thought, well, can we use something which I've already got? So let's have a look at how the Kettering ignition system works, and we'll analyze these two coils because even though they look the same, there's actually an important difference between the two. So I'll explain all of that, and once we've got through all the boring theory, we'll have a play with the Jeep. So this is the circuit of a typical Kettering ignition system, named after Charles Kettering, who developed it. I think he was part of GM, I think, and it goes back to the 1920s at least. So the basis of it, of course, is the coil which I've shown you before, and the circuit is thus. Now what happens is we've got the car battery here, which typically 6, 12 or maybe 24 volts, the coil, a spark plug. Now obviously if it's a multi-cylinder engine it's going to have a distributor and numerous spark plugs, but that doesn't concern us here. And a set of breaker points, which if you've worked on vintage ignition systems you would recognize thus. And the way these work, as the distributor shaft rotates, the cam rubs against this, well, lever if you like, and it opens and closes the contacts, and each time the contacts open is when the coil actually fires. And in conjunction with that is a condenser, which is this. This one measures 0.25 microfarads, which is fairly typical. So when we turn the ignition switch on, which is this, current flows from the battery through the primary winding of the coil, through the breaker points and to earth. Now the ignition coil is essentially a transformer, and the primary winding has a few turns and the secondary winding has a lot more turns. We're looking at sort of roughly about 100 times more turns. So by transformer action, whatever voltage appears on the primary coil is going to be stepped up by that turns ratio. Now there's a little bit more to it. When we apply current to a coil, the energy is actually stored in the iron core of the transformer, or induction coil if you want to call it that. And what happens is the build-up of current is not instantaneous. So if we do a simple graph, current, which is I, and time, the current build-up is actually exponential over a period of time, which is a couple of milliseconds. And when we get to a certain time, the current is going to level out and the energy will have reached saturation point. That is to say, we can keep putting more current into the coil for a longer time, but it's not going to do anything except make the coil get hot. So what we want to do is remove the current at about this point. That will make for best efficiency, because we've put as much energy as we can into the coil but no more. So we'll get our strongest spark, if you like, at this point. So that's when we want the points to open. And incidentally, this period here is what's known as the dwell, and if you've ever set up this kind of ignition system, your service manual would talk about dwell angles, and that's what that is. If we have a short dwell angle, we can see that there's not so much energy being stored in the coil as there could be, and the spark will be weaker. So the ideal dwell angle is going to be about there. So before the coil saturates, and yeah, no less or no more. Alright, so when the points open, this is where all the interesting things happen. The magnetic field in this core suddenly collapses, and if this was not controlled, the voltage which would appear across this primary coil would actually be infinite. But in practice, because of coil losses and other things, it isn't. But to cut a long story short, even though this might be 12 volts, appearing across this coil can be something like 300 volts. And it doesn't take long to realise that if we've got a ratio of 1 to 100, then this is going to be 30,000 volts, which will fire the spark plug quite nicely. And associated with the points opening is the condenser. Now its purpose is to control the rate at which this magnetic field collapses, because if it's too fast, as I said, the voltage would be infinite, and what happens is then the high voltage just arcs across the points, and that's why you'll see a spark if you haven't got the points capacitor there. Now what happens is the points capacitor or condenser, it slows down the rate of the voltage as it appears across the points when it opens. So the capacitor actually works opposite to a coil. So if we look at another boring graph, so this is the current and this is the time. So the capacitor initially appears as a short circuit, and as soon as the points open, current flows through the capacitor. Capacitor charges up over time, and it slows down the rate of which the magnetic field collapses. So that's the basic Kettering ignition system. Now, I showed two coils. What's the difference? Well, one of these coils, actually this one, even though it looks the same, is actually designed to be used with a ballast resistor, and this is a ballast resistor. Typically it has a resistance of about 1.5 ohms, and that's connected here in series with the current supply to the coil. And putting a resistor here, you can imagine, well, it's going to reduce the voltage to the coil, and yes, it does. So the difference between the resistor coil and the standard coil is that the resistor coil is actually a lower voltage coil. We're looking at sort of a rating of something like 6 to 9 volts. So the current flow through the resistor drops the voltage to, let's say, 6 volts. And the next question is, why would you want to do that? Well, it comes down to another feature which is used with this type of, let's say, enhancement of the Kettering ignition system. If we bridge out this resistor during the starting of the car, we can see that it will compensate for the voltage drop across the battery, because when we're pulling 150 odd amps from the car battery, the voltage is going to fall, and it might be 9-10 volts, something like that. Now if we've got a standard 12 volt coil here, obviously the voltage to the coil is going to be less, the spark's going to be less, and it's going to be harder to start the car. So by having an extra set of contacts on your ignition switch, which are bridged only during the start position, the resistor is shorted out and the full battery voltage goes into the coil, and we get a stronger spark, which is just what we need when we're cold cranking in freezing weather or something like that. A practical point is this coil has to have some DC resistance, whether there's a resistor or not. The reason for that is, taking the standard no resistor coil, if you turn the ignition on and the engine's not running, chances are the points are going to be in the closed position, and a horrendously high current is going to flow through that coil and burn it out. So it's got to have some resistance in it to limit the current. It's about, I did measure the resistances of these coils. The standard coil, standard 12 volt coil is 3.4 ohms, and the resistor coil I measured at 1.5 ohms. So the 12 volt resistor is 1.5 ohms, and you can see by simple voltage division theory that 1.5 ohms here and 1.5 ohms there is going to give you 6 volts across the coil. So that all works out. So with 3.4 ohms, the maximum current that can actually flow is about 4 amps. And we've got to have this resistance, otherwise the points would burn up, the coil would burn out, and all sorts of bad things happen. So with that all explained, my theory is that the coil meant for use with the resistor should in theory work on a 6 volt electrical system. So what I want to do is temporarily connect the resistor coil into the 6 volt electrical system, measure its current with the points closed, make sure that's all okay, and then start the engine and see what happens. And I should also say, before we get that far, is I have actually tried a 12 volt coil in a Citroen 2 CV, which was 6 volt, just as it was diagnosing a fault. The car wouldn't start, and all we had was a 12 volt coil, so I thought, well, it would probably give enough spark to fire a spark plug even if it's only at low speed, and it did. So I'm thinking that this is going to work, but we'll go through it and confirm it all and see how well it works. First thing I'll do is measure the primary DC resistance of these coils, just to see what we're working with. Now I think this is the Yeah, this is the 12 volt used with resistor coil, and I think it should be around 1.5 ohms. Okay, yeah, allowing for about 0.2 ohm lead resistance. Okay, so 1.5 ohm for the resistor coil. For the standard 12 volt coil, if I can get a reading. Okay, so if we take 0.2 of an ohm off that, about 3.3 ohms. Okay, which is what we'd expect. Now the coil that's in the Jeep itself, I'm not going to pull the coil out because it's a bit inaccessible. Well, I mean, not compared to a modern car, of course, but I don't need to take it out for this. Okay, so yeah, roughly taking into account lead resistance, about 1 ohm, a little bit more than that. Okay, so what we'll do next is measure what the DC current is, and I'll set up some clip leads for that. First thing to do is see what the current is on the existing 6 volt coil, which we measured to be about 1 ohm. Okay, so that's come up to 5 amps, and the reason it's not 6 amps is because of the wiring resistance. And as what we'll do next is measure the current of the resistor coil. That's about 3.7 amps. Okay, and remember this coil had high resistance, 1.5 ohms. And we'll now finally look at the current of the standard 12 volt no resistor coil, and that with its resistance, I think I said it was about 3.6 ohms. Current at 6 volts is about 1.8 amps. So I don't think that's going to give a strong spark, but we'll try it out anyway. So I'll set things up for the resistor coil, and we'll start the Jeep. I've wired up the 12 volt resistor coil, so I'll apply current and see how well it works. Well, I think that would certainly get me home. So I'll put the standard 12 volt coil in and see how good or bad that might be. Okay. So positive and negative. Alright, let's see what happens with the lower spark power. Well, there you go. 12 volt coil does work. I'm pleased to confirm that. So I mean, I can use either of these coils as an emergency get me home kind of thing, but yeah, obviously the 12 volt resistor coil is the one to go with, because that's closest to the characteristics of the original 6 volt coil. But having said that, your standard 12 volt coil will also get you home. Yeah, so the point has been proven.